Functions. Functions is one of the important prerequisite, basic concept required for engineering mathematics. Because if you want to understand calculus concepts, first of all, you need to understand the concept of function. Okay. Functions can be discrete functions or continuous functions. Okay. In calculus, we mainly concerned with continuous function. Discrete functions are studied by computer science students for their subject called discrete mathematics. Okay, so let us understand the entire story of functions as a review. Okay, so let us see the definition of a function. What is a function? See, a function from set A to set B is a rule. It is a rule which assigns every element of set A to exactly one element of set B. So if you are having a rule which assigns every element of set A to exactly one element of set B, then such a rule is called function. Then such a rule is called function. We say that f maps A to B is a function. Okay. So if you see this example, suppose you are having a set A and another set B, and we are having a rule. Say it is having say 1, 2, 3 element, and it is having say element A, B, C, D. Now I have a rule which assigns 1 to A, 1 to B, 2 to C, 3 to C. Is it a function? See, go with the rule. What the rule should do? Every element of set A should be used. Every element of set A is used, fine. Every element of set A is assigned to exactly one element of set B. But this element is assigned to two elements. So these assignments are there, no? A, B. These are called images. What are they called? Images. That is, for one element we are having how many images? Two images. This is wrong. For one element we should have exactly one image in B. Therefore, it is not a function. Simple, sir. Every element of set A should be used, and for one element we should have exactly one image. That's it. Nothing more than that. So if I give one more example like set A, set B with same 1, 2, 3 elements and same A, B, C, D element, and 1 goes to A, 2 goes to A, 3 goes to B. Is it a function? Obviously it is a function. Suppose if I give one more element in A like 4, it is not a function because 4 is not used, not a function. Not a function. Okay. Now look at this. Suppose if you are having A and B, 1, 2, 3, A, B, C, D. 1 is going to A, 2 is going to A, 3 is going to B. Is it a function? Obviously, it is a function. Some people are worried about this CD. See, my dear friend, I said every element of A should be used. I never said every element of B should be used. Okay, so it is not necessary. So if every element of B is not used, then we call it as into function. What is it called? Into function. Now suppose if you are having example like 1, 2, 3, AB, and a rule like this, 1 to A, 2 to A, and 3 to B. Now what is it? It is a function. Also every element of B is used. Okay, so we call such function as onto function. We call it as onto function. Is the idea clear? And one more concept here which we need to know is, suppose 1, 2, 3, A, B, C, D. 1 is assigned to A, 2 to C, 3 to B. Is it a function? Every element of A is used, and for every element there is exactly one image in B. Fine. It is not onto because D is not used. Okay. But if you observe, there is one more specialty of this particular function. 1, 2 are two different elements, and one image is A and two image is C. Two different elements are having two different images. If you see this example, different elements are having same image, but here different elements are having different images. Such function is called one-one function. So these are some basic functions one need to know. One-one function, onto function, and what is a function. First, these three things if we need to understand. Before proceeding to definitions, we try to fix the terminology. We try to understand the terminology. Okay. Now the terminology. Suppose f is a rule from set A to set B, which is a function. That is, every element of set A is assigned to unique element of set B. So it is a function. then this A is called domain. Set A is called what? Domain. And generally people feel B is codomain. I mean B is range. No, B is not range, it is just codomain. B is codomain. Now look here, what actually this function will do? It will assign every element to a unique element of set B. We denote it as fx. We denote it as fx. We can also denote it by some new symbol like y. Y is just a symbol we use. Y is equal to fx. So x is assigned to fx. So this fx is what is called as image of the function. This fx is called what? Image of the function. Am I clear? Fx is called image of the function. And for this fx, x becomes pre-image. X becomes pre-image. So please remember these terms. Okay, I may be covering. Sorry. So this is the story. So A is domain, B is codomain, fx is the image, and x is pre-image. See, for fx, x becomes the pre-image. See, just like when you see in mirror, what you see inside the mirror is your image, and for that image you are the pre-image. That is the basic idea. So this basic terminology one should know. So if you see previous example, so this is a function, right? This is a function. See, A is image of 1 and 2. See, for 1 and 2, A is image. And for A, the pre-images. What are the pre-images for A? The pre-images for A are 1 and 2. Like that. For B, what is pre-image? 3 is the pre-image. And for C and D, there are no pre-images. So if there are some elements for which pre-images are not there, then it is not onto function. That is simple logic. Is the idea clear? Now we need to understand what is range. See, this is set A and this is set B, and this is a rule. F is a mapping from set A to set B. As I told you, A is called domain and B is called codomain. B is called codomain. And A is called what, sir? Domain. See, it is not necessary that the entire A is mapped to entire B. Only part of B may be mapped. Okay. So the part to which A is mapped is what is called as range. This is what is called as range. That is, A is mapped to only this part. This is what is called as FA, which is range. This is range. For example, if you are having 1, 2, 3, A, B, C, D, 1 is mapped to A, 2 is mapped to A, 3 is mapped to B. Okay, then the range is not A, B, C, D, it is just A, B is your range, because function is mapped to only these two elements. So that is range. We denote it by FA. How you denote it? FA. And in general, FA should be subset of B. It's not equal in general, it is subset of B. Okay, and if FA equal to B, some cases it also happen that FA equal to B, then we call it as onto function. Then we call it as onto function. So that is it. These are the definitions. So let us simply write down the definitions for onto functions, one function, and we try to understand what is bijection, and we try to understand how to find inverse of a function. Now we understand what is onto function. Suppose you are having element 1, 2, 3 and AB. So 1 is mapped to A, 2 is mapped to A, and 3 is mapped to B. So this is onto function because every element in B we are able to find a pre-image. Okay. So what do you mean by onto function? What do you mean by onto function? For every element in B, you are able to find a X. For every element in B, you are able to find a element in A. Then if you can able to do it, then we call it as onto function. For every Y in B, we can find there exists X in A. How? Such that Fx is equal to Y. We can able to find this X such that this Y is Fx. Then we call it as onto function. That is a basic definition of onto function. Okay. Now one function. See, the basic idea of one is what? If two elements are there, they should be mapped to two different elements. Two different elements should be mapped to two different elements. For example, if I say x and y are two different elements, their images also must be different. These two must be different. That is, if x is not equal to y, then fx should not be equal to fy. That is the definition of 1 function. But this is difficult to verify, so we use an alternative version of this. Okay, that is called contrapositive of it, which is negation of this, then negation of this. That is, fx is equal to fy, then x equal to y. So this is how we verify whether the given function is 1. This is very simple to verify. Whereas if you want to verify, you need to consider all two combinations which are not equal and check their images are also not equal, which is difficult. So we use this technique to check whether the given function is 1 or not. Am I clear? Now we try to understand one more important idea, the bijective function. Now look here, 1, 2, 3, A, B, C. 1 is mapped to 2, 2 is mapped to C, 3 is mapped to B. Now this particular function is both 1, 1 and onto. Both 1, 1 and onto. Such 1, 1 and onto function is what is known as bijective function. Such 1, 1 and onto function is what is known as bijection. See, the advantage is, suppose this is set A and this is set B and this is F. Now what you do is try to go from B to A. Reverse you do it. 1, 2, 3. So B is mapped to, A is mapped to 1, B is mapped to 3, C is mapped to 2. The inverse relation is also a function. Even this is a function. Even this is also a function. Whereas if it is only 1, 1, suppose you check this AB, this is how my function is defined. Now try to revert it. 1, 2, 3. A should go to 1, 2, B should go to 3. Is it a function? It is not a function. Means it is only onto, but the inverse is not a function. Just a relation. Inverse is just a relation, but not a function. But when it is 1, 1 and onto, the inverse fellow will also be function. And only the function which is 1 and onto, that is bijection, is invertible. Means inverse also will be a function. This is a function, inverse also will be a function. That is the rule. So the rule is F inverse exists, means F inverse exists means F inverse is also a function if and only if F is 1, 1 and onto. See, inverse can be a relation, but it is a function if and only if the given function is 1, 1 and onto. Otherwise it is not possible. Is that clear? So we can take simple examples. F is a mapping from natural numbers to natural numbers with definition fx is equal to x minus 3. You need to check whether it is 1, 1 onto. Okay, the fate of the function we have to check. First of all, whether it is a function or not. My dear friends, please remember, function means for every value of x in domain, we could able to find a image in codomain. So I take a value of x in domain, that is f1, x, because n means 1, 2, 3 and so on. No? I take 1. f1 is how much? 1 minus 3, which is minus 2. And this minus 2 should belong to codomain. Then only it is a function. What is codomain in this case? Which is natural number system, 1, 2, 3 and so on. So this minus 2 belongs to codomain is correct or wrong? No. Because codomain is natural number system, which is wrong. So it is not a function first of all. It is not a function. So this is a discrete function because natural numbers to natural numbers you are going. Okay. Now let us take one more example. Again discrete function. F is a mapping from z to z. I define it as fx is equal to say 2x plus 3. Function, obviously integer, na? Z is integer, this is also integer. So if you take x is integer, 2x plus 3 is also integer. So that is image also integer. We need integer only, na? Image should be integer. So fine, it is a function. No problem. Now we need to check whether it is 1, 1 or not. How to check 1, 1? See, 1, 1 means what, sir? We need to take some fx1 is equal to fx2 and we have to prove x1 equal to x2. Then it's 1, 1. Just write down 2x1 plus 3 is equal to 2x2 plus 3. 3, 3 gone. 2x1 is equal to 2x2. 2 to gone, x1 equal to x2. Oh, wonderful. It is 1, 1. Now you want to check whether it is onto or not. See, the idea for onto is, for every element in codomain, we could able to find an element in domain. That is pre-image you could able to find. So originally this fx we write fx as y, no? So let us call it as y. That is y is equal to 2x plus 3. Now write x in terms of y. Write x in terms of y. Simple calculation. So 2x is equal to y minus 3. That is x equal to y minus 3 by 2. This x must be pre-image. So pre-image must be what? It should present in domain. So is it integer always? Is it integer always? For every y, this should be integer. Correct or wrong? Let us take y is equal to 2. Then what is x? 2 minus 3, that is minus 1 by 2. Is it integer? No. So no. Therefore, it is not onto. Is the idea clear? Like that. Let us take one more example. Example. F is a mapping from R to R, defined as fx is equal to 2x plus 3. Now here it is R to R, real numbers to real numbers. So such functions are called continuous functions. See, when it is discrete function 1, 2, 3 map to A, B, something like this, we can do it. We can just show it like this. But when it is a continuous function like this, how to show it? We'll see it after this example. Okay, how to discuss whether it is a function or not for continuous functions also we discuss. Now this is a function or not? Because x is real number. Then 2x plus 3 is also real number. So it is a function. Verification done. 1, 1, same fx1 is equal to fx2. That means 2x1 plus 3 is equal to 2x2 plus 3. These two cancel. 2x1 is equal to 2x2 means x1 is equal to x2. So it is 1, 1 function. Now you need to check whether it is onto or not. Because when it is 1, 1 and onto, then only inverse will be existing. Okay. Onto means write y is equal to 2x plus 3. No. Write x in terms of y. So what is x? Y minus 3 by 2. Now see the idea, sir. This is x mapped to fx. We call it as y. That is a y in terms of x. Reverse you want to see. For y you need to find x. So what is this x? F inverse y. So this x which you got is actually f inverse y. That means f inverse y is equal to y minus 3 by 2. See, clearly it is on to, no, because y is real number means y minus 3 by 2 is real number. Therefore, it is on to is done. Once it is on to, finding inverse is also same process. You can just continue. F inverse y is equal to y minus 3 by 2. This y is dummy variable. You can put t, p, l, anything. You can put x also, dummy variable. X minus 3 by 2. Because it is on to and 1, 1, we could able to find inverse of the function. It is done. Okay. So this is the method for finding inverse of a function. But so far we taken only this kind of circles and small single element, because when we consider discrete function this will work. But for continuous functions we cannot show elements like this. Now how can you write real numbers like this? Okay. So for that what we do generally is we plot the graph. For continuous function we plot the graph on xy plane. Okay. See, of course, if it is a function, the graph will be representing a function. But don't expect that every relation is a function. There is a relation between x and y. Don't expect that that relation is a function. Okay. For a relation between x and y, we can draw a graph, but this need not represent a function. Okay. Some of the relations may represent functions. Okay. So we have a beautiful test also for this called vertical line test. Okay. So what this vertical line test says is the given relationship between y and x. Okay. If you plot that graph, okay, it represents a function if a vertical line drawn cuts the graph only at one point. Okay, the vertical line drawn cuts the graph only at one point. For example, if you see this particular example, I given two graphs. For this blue one, light blue one, it cuts only at one point. But you see this dark blue one, if you drop a vertical line here, it will cut the graph at 3 points. That means for this element, we are having 3 images. Okay, not 3, 4 images. So can it be a function? No. So a relation between x and y can be plotted as a graph. That is a function or not? How can you verify? Using this vertical line test, you can verify. Okay, let us see the vertical line test. The vertical line test. A curve in xy plane is a graph of a function if and only if no vertical line intersect the curve more than once. So if you drop any vertical line, it should intersect the graph only at one point. But here it is intersecting the curve at 2 points. Therefore, it is not a function. Okay, this curve is not representing a graph of a function. Whereas the second one, you drop vertical line anywhere, it will cut the graph only at one point. Therefore, it is a function. Whereas this is not a function. So we also have a beautiful test to check whether the given function is 1, 1 or not. Let us see that. Now the horizontal line test. A function is 1, 1 if and only if no horizontal line intersects its graph more than once. So if you drop a horizontal line, if it cuts the graph at 2 points means, see, if it cutting at 2 points means for this point, this is the image. For this point also the image is this one. That is, for 2 different points you are getting same image. For 2 different points you are getting same image. Therefore, it is not 1, 1. So the horizontal line test can tell you whether the given function is 1, 1 or not. Vertical line test can tell you whether the given curve relation between x and y is a function or not. Clear? Now look at this example. F is a mapping from R to R where fx is equal to x square. First of all, whether it is a function or not. See, function means for every value of the x in domain, we get able to find an image. So we know this is a graph, y is equal to x square graph. So if you plot the graph, you are going to get this parabolic graph. So you take any x value, correspondingly I can get a functional value. Okay, so for every value, that is a vertical line, if you drop a vertical line anywhere, it will cut the graph only at one point. So obviously it is a function. It is a function. For every x value, I got a corresponding y value. For every x value, I got a corresponding y value. So it's a function. Now I need to check whether it is 1, 1 or not. Just now we referred, same example, it is not 1, 1. Why it is not 1, 1, sir? Because if you drop horizontal line, it will cut the graph at 2 different points. So it is not 1, 1. It is not 1, 1. Okay. Now is it onto? See, onto means what, sir? For every value of y in codomain, for every value of y in codomain, you could able to find a x. So y values are this. See, this is y axis now. Y axis represent your y values. Y axis represent your y. See, for every y value, you could able to find a x. See, this is a y value. For this, can you find a x value corresponding? There is no graph now. So we don't find any graph for negative values of y. That is, this value you are not going to get any x value correspondingly. That is, for every x you are not going to get negative values of y. Therefore, it is not onto. So same horizontal line test will help you for this also, because for this, if you are having means that should cut somewhere. Am I clear? It is not cutting anywhere means obviously there is no graph. Okay, for negative y values means what? It is not onto function. But don't think that fx is equal to x square is bad. Fx is equal to x square with f maps R to R is bad. But if you take the same function, fx is equal to x square with f maps R to R plus union 0. F maps R to R plus union 0. Now this time what is happening? You are mapping from R to positive only. That is, R to positive And I mean, not positive here, it is non-negative real numbers, we have to say. Non-negative real numbers. Non-negative real numbers. So obviously for every y value, because this is your codomain. Previous case, codomain was this entire thing. So for some values I am not able to find any x. But here the codomain is only non-negative real numbers. That is, codomain is from here to here only. This is your codomain. And for every codomain I am able to find pre-image. For every fellow I have corresponding pre-images. Okay, if you drop, these fellows will be pre-images. These two fellows will be pre-images for this fellow. Okay, you need to drop horizontal followed by vertical to know that particular thing. Okay, that much work we need to do. Got it? So this fellow now becomes, this function becomes onto function. This fellow becomes onto function. Now is it 1 1? Still it is not 1 1, because if you drop a horizontal line, it is cutting the graph at 2 points. Therefore it is not 1 1. It is only onto. So by making this R plus union 0, that is non-negative real numbers, as codomain, you made it onto, but it is still not 1 1. See, not 1 1 you can check by graph, or you can simply see two values as, because f at minus 1 is 1 minus 1 square, that is plus 1, and f at 1 is also 1 square, which is plus 1. That is, two different fellows are going to same image. Therefore it is not 1 1. Now let us make it better by changing domain. Let us see that. Now this time it is, domain is R plus union 0, that is non-negative real numbers. What is it? Non-negative real numbers. This is not entire real numbers, sir. It is only non-negative real numbers. So 0 to infinity. And y values are also 0 to infinity. We are only talking about the first quadrant now. Now what is y? Y is equal to x square. This is the graph. Now there is no negative values, because your domain is only from here. We need to consider only this much graph. Now this particular function is 1 1. Obviously now you drop a horizontal line anywhere. It will cut the graph only at 1 point. Now it becomes 1 1 and also onto, because see, if this is your codomain, right? For every codomain value I'm able to find a corresponding pre-image. For every codomain value I'm able to find corresponding pre-image, like this. So it is onto also. See, same fx is equal to x square. I not changed the function, only domain and codomain made it. Okay, 1 1 and onto. See, it depends on domain and codomain, my dear friend. It does not depend on y is equal to x square. Please remember. Okay, now because it is 1 1 and onto, f inverse exists. In this case, f inverse exists. Means when domain is this and codomain is this, f inverse exists. And what is f inverse? Y is equal to x square, na? So that is y in terms of x. Y in terms of x. So write x in terms of y. Write x in terms of y. Then what happen? X will be, actually, see, when x square is equal to y, x will be plus minus root y. But you are in the first quadrant, you don't take, ignore minus root y. Therefore x is equal to plus root y. So this would be the inverse function. This would be the inverse function. We can write now f inverse y. That is, f inverse y is root y, or f inverse x is equal to root x. This is the inverse function. So for y is equal to x square, inverse exists if you are having domain and codomain defined like this. So always it depends on domain and codomain, my dear friends. Okay. So for y is equal to x square, inverse does not exist. We can't say like that. You need to see what is your domain and what is your codomain. For that, it will happen. See, actually, when you are having y is equal to x square, we can't find inverse for this. But for this, inverse is there, and that is y is equal to root x. Okay, y is equal to root x, you can write, or what is it? Y square is equal to x. When you plot, this is what going to happen. This would be y is equal to root x. And this is y is equal to x square graph. So in the first quadrant, these two fellows are inverses of each other. These two fellows are, this is y is equal to root x. This means y is equal to root x. We can write like this. And the original one is y is equal to x square. This one is y is equal to x. Okay, and we have a beautiful technique also to draw the inverse of a function if it exists. Let us see that. The graph of f inverse x is obtained by reflecting the graph of y is equal to fx. Suppose this is y is equal to fx is your graph, original one, and you want to find the inverse graph of this particular fellow. You need to reflect this y is equal to fx about y is equal to x line. This line of y is equal to x line, if you reflect about it, that is y is equal to x line, you keep it as mirror, the mirror image, this is f inverse x, the red line is f inverse x graph. Okay, so similarly in the previous example also, don't see the scale, sir, you'll get confusion. Don't go with the scale, just try to understand the idea. Okay, for example, okay, I'll put this way. Y is equal to x square graph would be something like this. This is y is equal to x square graph. The inverse graph, if you draw, don't go with the scale. I told you, na, don't go with the scale. Just see the diagram. The inverse fellow graph would be like this. So it is like, mirror image. So y is equal to x, if you take it as mirror, for this fellow, this will be the mirror image. Okay, I'll just draw it with red, then you will understand. See this one. Mirror image. Like that. Suppose if you are having some graph, okay, something like this, the mirror image about y is equal to x. Or suppose you can take different colors. Suppose your graph is something like, okay, like this. Okay, then we need to know what is y is equal to x line. What is y is equal to x line? This is y is equal to x line. So the inverse fellow would be like this. That is inverse fellow. So you can get the graph of inverse fellow if at all it exists. So here in this previous example, when you see for y is equal to x square, inverse is y is equal to root x, it exists if the domain and codomain are defined like this. But if you take R to R, inverse does not exist. Okay, that is not inverse relation, but it is not inverse function. Please remember that. Actually here, I'll just tell you. Suppose y is equal to x square is your function. Okay, see, x is equal to plus minus root y you are going to get. Actually, x is equal to plus root y defines a function, and x is equal to minus root y is another function. Okay, this is also a function, this is also a function. Am I clear? These are two different functions which are obtained from this. Two different functions. For this, we need to take the original function from r plus union 0 to r plus union 0. Okay, whereas for this we need to take original function as r minus union 0 to r plus union 0. So this would be the function which is obtained with this domain and this codomain. So the domain and codomain will decide, okay, the nature of inverse function. Am I clear? And y is equal to x square, don't say whether inverse exists or not directly, you need to ask for domain and codomain. And suppose if he gives y is equal to x square and asks you to find f inverse x, then we assume that the domain and codomain are defined in such a way that inverse exists. Am I clear? For example, if your domain is having only one element and codomain is having only one element, obviously inverse exists. I can have like that. Is it clear? So we need to always understand that particular point. Is the idea clear? Okay, this is about inverse of a function. See, once a domain and codomain are given and a rule is given, we can verify whether it is a function or not. But sometimes a rule will be given, like, fx is equal to 1 by x. And you need to identify for what values of x this will be a function, means this rule will be a function. See, obviously here we can understand when x is not equal to 0, then it would be a function. So the domain is x not equal to 0. That, or in other words, you can say like, real number system minus 0. Or you can have a question like fx is equal to root x. What is domain for this? See, x negative, then it is not defined. Am I clear? So domain must be what? X must be greater than or equal to 0. Non-negative real numbers we call it. Okay. Or if I say fx is say root x minus 3, if I say. See, this argument x minus 3 must be greater than or equal to 0. So what is domain? x minus 3 greater than or equal to 0 or x is greater than or equal to 3. Sometimes we need to identify what is for what domain this will be a function. This rule will be a function. Okay, like this. Now let us take one more interesting example. What is domain of this function? Okay, domain. See here it is root x minus 1 and it is root 3 minus x. Obviously x minus 1 must be greater than or equal to 0 and 3 minus x must be greater than or equal to 0. But what does it mean? X is greater than or equal to 1. Here 3 minus x is greater than or equal to 0 means 3 should be greater than or equal to x. If you combine these two things, because both must be happening, this is 1 should be less than or equal to x, less than or equal to 3. So this function is defined only in the range, in the domain 1 to 3. Closed interval we call it 1, 3. So the domain we can identify, means rule is given, you can identify when it is a function. Okay, so it would be one more very interesting idea. Now let us define the composite function. Suppose f is a mapping from a to b and g is a mapping from b to c. Then the composite function g circle f. First we write second function g, then we write first function. That is g circle f we write. Is a mapping from a to c defined as, we write g circle f of x is equal to g of fx. G of fx. So the story goes like this. This is a, this is b, and this is c. So f is a mapping from a to b, so it will change x to fx. And g is a mapping from b to c, it will change fx to g of fx. So g circle f is actually mapping from a to c. This is g circle f of x is directly mapping from a to c, which is g circle f of x is nothing but g of f of x. Okay, so let us see example. Now look here, fx is given as x square and gx is given as x plus 3. F circle g of x and g circle f of x we need to find. Now what is f circle g of x? F of g of x. See, what is gx here? Gx is x plus 3. Just put x plus 3 here. Now what is the nature of the function fx? Whatever argument you give, it will square that. So this argument will be squared. That is x plus 3 whole square you are going to. So this is f circle g of x. Now what is g circle f of x? G of fx. That is g of, what is fx here? X square. Now what is the nature of g? Whatever argument you give, it will just add 3 to it. So whatever argument is there, plus 3 it will do to the argument. What is the argument? X square plus 3. And clearly you see that f circle g is not equal to g circle f. In general, f circle g and g circle f need not be same. And actually sometimes, even if f circle g is there, g circle f need not be defined, or g circle f is defined, then f circle g need not be defined. For example, f is a mapping from a to b and g is a mapping from b to c, then g circle f is possible. But if you want f circle g, first you write g, right? G means b to c, but f is from a to b. So if this c goes somewhere, then we can have f circle g mapping. So this mapping is possible when c is equal to a, then only it is like this. This is possible, that is f circle g is possible when c is equal to a. So we need to understand that both need not be defined. Even if both are defined, they need not be equal. Okay, now we try to understand one interesting aspect here. What is domain of composite function? Okay, let us understand that. Now let us see this particular problem. What is domain of g circle f of x? Domain of g circle f of x. So here g circle f of x means g of f of x. See, whenever this particular question is asked, first we need to find domain of f, the inner function. What is domain of f you have to find. So the domain of f is, fx is root x, no? So domain of f, if you want, because fx is equal to root x, so this is defined when x is greater than or equal to 0. So this is domain of f, x greater than or equal to 0. Keep that in mind. Okay. Now what we need to do is, we need to go for G circle f of x. G circle f of x. What is G circle f of x? G of, what is fx, sir? Fx is root x. Then what is g of root x? See, x, whatever argument is there, under root 2 times 2 minus that argument. So it is under root 2 minus root x. This is G circle f of x. So now this particular fellow's domain means this 2 minus root x must be greater than or equal to 0. That means, or you can say, root x must be less than or equal to 2. Yani x should be less than or equal to 4. But you should not take just x is less than or equal to 4. Even you have to include these two. Because when f is defined, then only this g should be defined. So the domain of G circle f will be x greater than or equal to 0 and x less than or equal to 4. That is combinedly 0 less than or equal to x less than or equal to 4. So generally what people do is they take this as domain, but they miss this particular part. We should include both. Okay, because when this is defined, then only G circle f is possible. Okay, so you need to combine these two. So this is domain of G circle f. This is domain of G circle f. Now let us see one more example. Fx is given, gx is given. Find domain of f circle g of x. Okay, so it is f of f circle g of x means f of gx. So what we do is first find domain of g. What is domain of g? You have to find that. Domain of gx means this is gx is what? 3 by 2x minus 1. That means 2x minus 1 should not be 0. That is, x is not equal to 1 by 2. Now go back to f of g of x. That is f circle g of x. That is f of g of x, which is nothing but f of, what is gx? 3 by 2x minus 1. Now what is f? 2 by x minus 1. That is whatever argument you give, 2 by argument minus 1. What is argument? 3 by 2x minus 1 minus 1. Now you won't need to find domain means the denominator should not be 0. That is 3 by 2x minus 1 should not be 0. That means 3 by 2x minus 1, okay, is, okay, let us put equal to 1, easy to solve. Okay, otherwise you'll get confusion. Let us solve it and last we put not equal to. Let us solve this. So that means 2x minus 1 is equal to 3. That means 2x is equal to 4. That means x equal to 2. So that means x should not be equal to 2. So generally people feel this is the domain, but this is not just the domain, sir. Even you need to include these two. That is, the domain is x not equal to 2 and x not equal to half. So if you want to write, you can just write from minus infinity to half, union, half to 2, union, 2 to infinity. Like that. Let us take one more interesting example. Now sine 1 by x. See, generally people feel it is a single function. Actually, it is not a single function. It is composition of two functions. The two functions are, one is gx, okay, which is 1 by x. The other one is hx, which is sine x. So actually it is h circle g of x. H of gx. What is gx? 1 by x. H of 1 by x means sine 1 by x. So this function is actually composition of two functions. It's not a single function. So generally sine is very good function. So domain is for all x they feel. But you need to consider the inner function. So here when you see 1 by x, the domain should not be including 0. But for this, x should be any real number. So when you take intersection, 0 will be removed. So r minus 0 will be your domain for this. So domain is r minus 0. We need to understand that. Am I clear? So sine 1 by x is not defined for x equal to 0. Sine 1 by x is not defined for x equal to 0. So x should not be 0. That is domain. You can write like this, or you can say r minus 0. Okay. So this was a gate question. Of course, this question is about discontinuities. Okay, we are talking only about definition of the function. But if you don't understand definition, the discontinuities part cannot be handled. So I want you to understand this f circle g of x for this. Actually, if you observe, fx is defined for x less than 0 and x greater than 0. Gx is defined for x less than or equal to 1 and x greater than 1. So we need to understand this entire story in these intervals. Okay, there is a point 0 and there is a point 1. So before 0, after 1, and between 0 1, the definition is changing. So we need to write the definition of f of g of x for each of these intervals. Now let us see what is f of g of x for x less than 0. For x less than 0, this is the range x less than 0, and this is between 0 to 1, and this is for x greater than 1. Okay, equal to part we can take care later. Okay, because less than or equal to 0 is there. So similarly, less than or equal to 1 is there, so you can include like this. Okay, now f of g of x. What is the definition of f of g of x? What is gx? Gx for x less than 0. So x less than 0 means it is less than 1 only, na? This part we have to do. See, for less than 1, see, less than 1, its definition is minus x. So less than 0 means still it is less than 1 only. So it is minus x. This definition will come. So f of minus x. Now x is less than 0 means minus x will be greater than 0. Correct or not? When x is less than 0, minus x will be greater than 0. So x greater than 0, how fx is defined? It is defined as x square. So the definition would be, okay, whatever fellow, minus x is greater than 0, no? So it is minus x whole square, square of that function. Because for x greater than 0, how fx is defined? Square of that fellow. Whatever is here, square of that fellow. So it is minus x square, which is nothing but x square. So the definition for x less than 0 is x square. Now from 0 to 1, let us see f of g of x. What is f of g of x for 0 to 1? See, gx is still we are talking about x less than or equal to 1 only. So gx up to 1, it is minus x only. So it is f of minus x. But now it is x is greater than 0, means x is positive. So minus x is negative. So this minus x is negative. So x less than 0, what is the definition of fx? So when this fellow minus x is less than 0, what is definition? When this argument is less than 0, 1 minus of that argument. So you get 1 minus of that argument. Because this argument is less than 0, 1 minus of that argument. So what is that argument? Minus x. So it is 1 minus of minus plus x. So it is 1 plus x. Now for x greater than 1, you have to see third case, f of g of x. What is f of g of x for x greater than or equal to 1? Now gx for x greater than 1 is defined as x plus 1. So we have to write f of x plus 1. So when x is greater than 0, x is greater than 1, x plus 1 is also greater than 1. Obviously it is greater than 0. So we have to use this condition. So what is f of x plus 1? Argument is greater than 0 means square of that. So it is x plus 1 whole square. So the definition of f circle g of x is not in a single interval, it is in 3 intervals. One is for x less than or equal to 0. What is it? It is x square. And the other one is for 0 less than x less than or equal to 1. It is 1 plus x. And for x greater than 1, it is x plus 1 whole square. So the continuity need to be discussed in these 3 intervals. Let me take next slide. So this is your f circle g of x. The question was number of discontinuities in the interval minus infinity to 0, that is less than 0. But less than 0, it is polynomial, so continuous. So number of discontinuities in the interval minus infinity to 0 is 0. But if you want at x equal to 0, if you want to check what is left hand limit, what is left hand limit, put 0 here, it is 0. What is right hand limit? Right hand limit 0 is 0 plus 1, which is 1. So not equal. So discontinuous at x equal to 0. And again at 1 you have to check. At x equal to 1, what is left hand limit? Put 1 in this. 1 plus 1, that is 2. What is right hand limit? Put 1 in this. 1 plus 1, 2 square, that is 4. They are not equal. That is, for total function, number of discontinuities would be 2. What are they? Number of discontinuities are at x equal to 0 and x equal to 1. Total number of discontinuities equal to, or see, number of, or discontinuities, you say. Discontinuities are at x equal to 0 and 1. Therefore, number of discontinuities would be, if you want to find for total function, 2 discontinuities are there. But he asked in the interval minus infinity to 0, therefore, there are no discontinuities, 0 discontinuities. Okay, he asked because for minus infinity to 0. If 0 is included, we should have said 1. 0 not included, less than 0 is said, so it is good function. Is the idea clear? So for that, if you want to answer, first you need to know what is f circle g of x. Am I clear? Sometimes some basic ideas needed to understand. So what we try to understand in this particular video is, we try to understand what is function, what is one function, what is onto function, and how to find inverse of a function, and what is domain of a function, what is composite function, and how to find domain of a composite function. Is the idea clear? Thank you.